In January 2023, a team of astronomers published a paper in the journal Nature that sent a specific kind of tremor through the cosmology community. Not a dramatic claim of new physics or a sensational announcement, something more unsettling. A careful, rigorous analysis of the first deep field images from the James Webb Space Telescope showing galaxies that should not exist. Not galaxies that were unexpected or surprising, galaxies that, based on our best understanding of how the universe works, how stars form, how dark matter assembles into the gravitational scaffolding that holds galaxies together, how the cosmic web of structure develops from the smooth uniformity of the early universe into the complex architecture of today, should not have had time to form as early as they did, as large as they were, as bright as they were, and as numerous as they were. The specific claim, made with appropriate scientific caution, was that several of the early galaxies detected by Webb in its first deep imaging campaigns appeared to have masses comparable to the Milky Way, despite living at redshifts corresponding to the universe being only 500 to 700 million years old. The universe is 13.8 billion years old. Galaxies of Milky Way mass at 700 million years old are not just surprising, they represent a potential contradiction with the Lambda-CDM model, the standard cosmological framework, the lambda cold dark matter model that has been the foundation of our understanding of cosmic structure formation for nearly 3 decades. I want to take you through what the James Webb Space Telescope is, what it is measuring, what it found, why the finding is potentially significant, what the standard model of cosmology predicts about galaxy formation, and why those predictions are precise enough to be tested, and what the possible resolutions of the tension are. Some of those resolutions involve modifications to the standard cosmological model that are deeply interesting. Some involve astrophysical effects that do not require new physics. And some involve systematic errors in the analysis that are being actively investigated. But I want to begin with the telescope itself, because understanding what Webb can do that Hubble cannot is essential for understanding why these early galaxy observations are possible at all and why they are reliable enough to take seriously. The James Webb Space Telescope was launched on the 25th of December 2021 from the Guiana Space Center in Kourou, French Guiana, on an Ariane 5 rocket. The launch was the culmination of more than 25 years of development with a total mission cost of approximately $10 billion, making it the most expensive scientific instrument ever built. After a 30-day deployment sequence of extraordinary complexity involving 344 single point of failure events in the correct sequence, the sun shield unfolded to roughly the size of a tennis court, the 18 hexagonal primary mirror segments deployed and phased, and the instruments cooled to their operating temperatures of between 34 and 240 Kelvin. Webb reached its operational position at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth in the direction away from the Sunday. At L2, the gravitational pulls of the Earth and Sun balance the centrifugal force of the orbital motion, allowing the telescope to maintain a stable position relative to the Earth while always keeping its sun shield between itself and the Sunday. The sun shield reduces the solar heat flux at the telescope by a factor of approximately 1 million, cooling the primary mirror and instruments to the temperatures required for sensitive infrared observation. The primary mirror of the James Webb Space Telescope has an effective diameter of 6.5 meters, made up of 18 hexagonal beryllium mirror segments coated with gold. The collecting area is approximately 25 square meters, approximately 6 times larger than Hubble's 4.5 square meters. This larger mirror allows Webb to collect more light from faint distant sources, directly translating to the ability to detect fainter objects and obtain higher signal-to-noise spectra in shorter exposure times. The gold coating on the mirror segments is specifically chosen for its high reflectivity in the infrared. Gold reflects approximately 98 to 99% of infrared light. compared to approximately 85 to 90% for the aluminum coating used on Hubble's mirror, for a telescope designed to collect the faintest possible infrared light from the earliest galaxies. This difference in reflectivity is significant. But the most important difference between Webb and Hubble is not the mirror's size or coating. It is the wavelength range and the thermal design that makes infrared sensitivity possible. Hubble observes primarily in the ultraviolet and visible wavelengths from approximately 115 to 1,000 nanometers, with some near-infrared capability extending to about 1,700 nanometers, with the Wide Field Camera 3 installed during the last servicing mission in 2009. Webb observes primarily in the near-infrared and mid-infrared from approximately 600 nanometers to 28 micrometers. The wavelength range of Webb extends more than 16 times further into the infrared than Hubble's maximum. This difference is decisive for observing the very early universe because of the specific physics of cosmic redshift. As light travels through the expanding universe, its wavelength is stretched proportionally to the expansion of space. The stretching is characterized by the redshift z, defined such that the observed wavelength equals the emitted wavelength times 1 plus z. A galaxy at redshift z equals 10 has had its light stretched to 11 times the emitted wavelength by the time it reaches us. The hydrogen Lyman alpha emission line, the transition between the first excited state and the ground state of hydrogen at 121.6 nanometers, is the most prominent spectral feature in the spectra of star-forming galaxies. At redshift 10, this line is observed at approximately 1.34 micrometers. At redshift 15, it is observed at approximately 1.94 micrometers. Both of these are deep in the near-infrared, well within Webb's observing range. The same line observed at these redshifts with Hubble would be either at the very limit of Hubble's sensitivity or completely inaccessible. The Lyman break, the sharp cutoff in galaxy spectra at wavelengths shorter than Lyman alpha, due to absorption by neutral hydrogen in the galaxy's interstellar medium and in the intergalactic medium, is the primary photometric feature used to identify high redshift galaxy candidates. At redshift 10, the Lyman break falls at approximately 1.2 micrometers. Galaxies at this redshift are invisible in optical bands and faint in near-infrared bands below 1.2 micrometers, but bright in near-infrared bands above 1.2 micrometers. This dropout technique, identifying galaxies that are absent in short wavelength bands but present in long wavelength bands, has been used to find high redshift galaxy candidates since the 1990s. Webb's 4 science instruments are the near-infrared camera, the near-infrared spectrograph, NIRSpec, the mid-infrared instrument, MIRI, and the fine guidance sensor and near-infrared imager and slitless spectrograph, FGS, NIRS. For the early galaxy science, NIRCam and NIRSpec are the primary instruments. NIRCam is Webb's primary imaging camera, covering the wavelength range from 0.6 to 5 micrometers with high sensitivity and spatial resolution of approximately 0.065 arc seconds per pixel. It has a wide field of view of approximately 9.7 square arc minutes in each of its 2 modules, which can be used simultaneously to cover a total area of approximately 9.7 square arc minutes. For deep field imaging, NIRCam observes in multiple photometric bands simultaneously, building up multi-wavelength photometry of thousands of galaxies in a single pointing. NIRSpec is Webb's spectrograph, providing spectroscopy from 0.6 to 5.3 micrometers with resolving powers of 100, 1000, and 2700. Its multi-object spectrograph mode can observe up to 100 targets simultaneously using a microshutter assembly, a grid of 250,000 individually addressable shutters that can be opened and closed to select specific objects in the field. This multi-object capability is revolutionary for high redshift galaxy science. Instead of observing one galaxy at a time with previous space spectrographs, Webb can obtain spectra of hundreds of galaxies simultaneously in a single pointing. The spectroscopic confirmation of high redshift galaxies is crucial because photometric redshift estimates can be wrong. A galaxy that appears to be at redshift 10 based on its photometric colors might actually be a foreground galaxy with unusual dust reddening or a broadline AGN, or a stellar object with peculiar colors. Spectroscopic confirmation, measuring actual spectral emission or absorption lines and deriving the redshift from their observed wavelengths, provides unambiguous identification. Webb's NIRSpec has now spectroscopically confirmed galaxies at redshifts above 10, with the current record holders at redshifts 13 and 14 corresponding to the universe being approximately 320 and 290 million years old. Each spectroscopic confirmation is a direct measurement of an event from the first few hundred million years of the universe's history, a look-back time of over 13.5 billion years. The JADES survey, the JWST Advanced Deep Extragalactic Survey, was designed specifically to push to the limits of Webb's capability for studying the very early universe. It combines extremely deep imaging with NIRCam over fields totaling approximately 25 square arc minutes, with exposure times of days per field reaching photometric depths of approximately 30 AB magnitudes in each of 8 photometric bands. The JADE survey also includes deep NIRSpec spectroscopy, targeting the highest redshift and most scientifically interesting galaxies identified in the imaging. Together, JADE's imaging and spectroscopy provide a comprehensive census of galaxies from redshifts 4 to beyond 12, tracing the growth of galaxies across the first 2 billion years of cosmic history. The galaxies that have generated the most scientific discussion are not the highest redshift objects, but the massive early galaxies at redshifts 7 to 10. These are galaxies whose stellar masses, the total mass of stars within the galaxy, have been inferred from their infrared luminosities and estimated star formation histories to be of order 10 to the 10 to 10 to the 11 solar masses, comparable to massive galaxies in the local universe. The stellar mass of a galaxy is one of the most fundamental observational quantities in extragalactic astronomy, but inferring it from photometric observations of high redshift galaxies involves systematic uncertainties. The conversion from observed luminosity to stellar mass depends on assumptions about the stellar initial mass function, the distribution of star masses in a newly formed stellar population, the star formation history of the galaxy, the dust content and its effect on the observed colors, and the treatment of stellar population models, which describe how stars of different masses and ages contribute to the overall luminosity at different wavelengths. Each of these assumptions introduces uncertainty. The systematic uncertainty in stellar mass estimates for high redshift galaxies from photometric data is estimated at approximately a factor of 2 to 3. A galaxy inferred to have a stellar mass of 10 to the 11 solar masses might actually have a mass between 3 times 10 to the 10 and 3 times 10 to the 11 solar masses. This uncertainty is important for evaluating the significance of the tension with the standard model. Ready to change how you see the world? The specific tension between Webb's early galaxy observations and the predictions of the standard cosmological model is exactly the kind of anomaly that has historically preceded the most important advances in physics. The 12 principles I have assembled for understanding the fabric of reality are designed to help you think clearly about exactly this kind of situation, where the data is pointing beyond the current framework without yet specifying where it leads. Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me now describe the standard cosmological model and what it specifically predicts about the formation of early galaxies, because the tension with Webb's observations requires understanding the predictions at the level of detail where the tension actually lies. The Lambda-CDM model is the standard cosmological framework. Lambda refers to the cosmological constant the dark energy term in Einstein's equations that drives the accelerating expansion of the universe. CDM refers to cold dark matter, the non-baryonic, non-relativistic matter that provides the gravitational scaffolding for structure formation. Together, the cosmological constant and cold dark matter, combined with the known physics of baryons, photons, and neutrinos, describe the evolution of the universe from the Big Bang to the present day with just 6 parameters: the baryon density, the cold dark matter density, the optical depth to reionization, the amplitude of primordial density fluctuations, the spectral index of the primordial power spectrum, and the Hubble constant. These 6 parameters, measured with extraordinary precision from the Planck satellite's observations of the cosmic microwave background, determine the entire history of cosmic structure formation. The precision of the measurements is remarkable. The baryon density is known to better than 1%, the dark matter density to better than 2%, and the spectral index to better than 0.5%. Starting from these initial conditions, the Lambda-CDM model predicts the growth of structure through gravitational instability. Overdense regions grow over time by accreting matter from their surroundings. The growth is governed by the linearized equations of perturbation theory at early times and by the fully nonlinear equations of gravitational dynamics at later times. The evolution has been computed in exquisite detail using n-body simulations that track the trajectories of billions of dark matter particles through cosmic history. The physics of structure formation in cold dark matter is hierarchical. Small structures form first because the primordial density fluctuations have more power on small scales, and these small structures then merge to form progressively larger ones. This is the bottom-up assembly of cosmic structure that distinguishes cold dark matter from alternatives like hot dark matter, in which the free streaming of fast-moving particles erases small-scale fluctuations and produces a top-down formation history. The first dark matter halos form from density fluctuations that exceed the collapse threshold at redshifts above 20 when the universe is less than 200 million years old. These first halos have masses of approximately 10 to the 6 to 10 to the 8 solar masses. They are far smaller than present-day galaxies, which have dark matter halos of approximately 10 to the 12 solar masses for a Milky Way analog. The buildup from the first halos to galaxy-scale halos occurs through hierarchical merging. Small halos fall into larger ones, which fall into still larger ones, in a continuous process that spans cosmic time. The formation of stars within halos requires baryons to cool from the virial temperature of the halo, which is typically millions of Kelvin for massive halos, to the temperature at which molecular hydrogen can form, collapse, and fragment into protostars, which is of order 100 Kelvin. This cooling requires the gas to radiate energy, primarily through hydrogen and helium transitions at high temperatures and through molecular hydrogen emission at lower temperatures in the first halos. The rate of star formation in a galaxy is a strong function of the available gas supply, the cooling rate, and the feedback processes that can interrupt star formation by heating or expelling gas. Supernova explosions are the dominant feedback mechanism in low-mass halos. A young, massive star lives for only a few million years before exploding as a supernova, releasing approximately 10 to the 51 ergs of energy. This energy heats the surrounding gas and can drive outflows that remove gas from the galaxy. For the first galaxies at high redshift, the combination of efficient cooling, high gas densities, and possibly reduced feedback from the first generation of stars, which have lower metallicities and different properties from present-day massive stars, could lead to higher star formation rates than in present-day galaxies. The question is whether this enhanced star formation is sufficient to explain the massive early galaxies detected by Webb, the n-body plus hydrodynamical simulations that model galaxy formation in the Lambda-CDM framework, including the Illustris TNG, Eagle, and Fire simulations, have been calibrated against observations of the galaxy population from redshift 0 to approximately 5. They reproduce the galaxy stellar mass function, the galaxy size-mass relation, the star formation rate density of the universe, and many other observational constraints with reasonable accuracy in this redshift range. Extrapolating these models to redshifts above 7, where they have not been calibrated, is where the tension with Webb's observations emerges. The specific predictions of these simulations for the galaxy stellar mass function at redshifts above 7 are several to 10 times below the early observational estimates from Webb. The simulations predict that galaxy mass halos of 10 to the 12 solar masses, which are needed to host galaxies with stellar masses of 10 to the 11 solar masses, should be rare at these early times, with abundances several orders of magnitude below the observed galaxy candidates. The discrepancy is largest for the most extreme objects and depends sensitively on the stellar masses inferred from the photometric observations. The inferred stellar masses have uncertainties of approximately a factor of 2 to 3, which could reduce the tension significantly. But even at the lower end of the inferred mass range, the observed galaxy abundance significantly exceeds the simulation predictions. The stellar mass of a galaxy is one of the most fundamental observational quantities in extragalactic astronomy, but inferring it from photometric observations of high redshift galaxies involves systematic uncertainties. The conversion from observed luminosity to stellar mass depends on assumptions about the stellar initial mass function, the distribution of star masses in a newly formed stellar population, the star formation history of the galaxy, the dust content and its effect on the observed colors, and the treatment of stellar population models, which describe how stars of different masses and ages contribute to the overall luminosity at different wavelengths. Each of these assumptions introduces uncertainty. The systematic uncertainty in stellar mass estimates for high redshift galaxies from photometric data is estimated at approximately a factor of 2 to 3. A galaxy inferred to have a stellar mass of 10 to the 11 solar masses might actually have a mass between 3 times 10 to the 10 and 3 times 10 to the 11 solar masses. This uncertainty is important for evaluating the significance of the tension with the standard model. Despite these caveats, the tension has not dissolved as more data and more careful analysis have accumulated. Spectroscopic confirmation of massive galaxies at redshifts above 7 with stellar masses of several times 10 to the 10 solar masses has continued to mount through 2023 and 2024. The tension appears to be real, though its quantitative magnitude depends on the assumptions made in inferring stellar masses and the specific comparison to simulations. The scientific paper that received the most attention was by Labbe and collaborators, published in Nature in February 2023. They reported 6 photometrically selected galaxy candidates at redshifts from 7.4 to 9.1 with inferred stellar masses of 1 to 3 times 10 to the 11 solar masses in the first SEERS, Cosmic Evolution Early Release Science observations. If these masses are correct, the galaxies are forming stars so rapidly that they would have converted more than half of their available baryons into stars within the first few hundred million years of the universe's existence, an efficiency that exceeds what standard galaxy formation models predict. This star formation efficiency is the heart of the problem. In the standard Lambda-CDM model with standard stellar and AGN feedback, the fraction of available baryons that are converted to stars in a galaxy is limited by various feedback processes. Supernova explosions that heat and expel gas from the galaxy, radiation pressure from young massive stars that drives outflows, and energy injection from accreting supermassive black holes. These feedback processes ensure that, at most, a few percent of the available baryons in a dark matter halo are converted to stars. with the exact fraction depending on the halo mass and redshift. If the Webb galaxies have the stellar masses inferred from photometry, they must have converted 30 to 60% of their available baryons to stars, a factor of 10 to 30 more efficient than the standard model allows. Either the standard model of stellar feedback is wrong at early times, or the stellar masses are overestimated, or the dark matter halos hosting these galaxies are much more massive than the standard model predicts at those redshifts, or some combination of these. What do all these early massive galaxies mean? I want to explore the three most interesting possibilities because each one has profound implications for our understanding of the universe. The first possibility is that the standard Lambda-CDM model is correct, but the baryonic physics of galaxy formation at early times is different from what current models assume. Specifically, star formation in the early universe may have been dramatically more efficient than it is today, or the feedback processes that normally limit star formation may have been less effective. The early universe had a different interstellar medium than the present-day universe. The first galaxies had much lower metallicities. The heavy elements produced by nuclear burning in stars and ejected by supernova explosions had not yet been distributed through the interstellar medium. Low metallicity gas is less effective at cooling and fragmenting than metal-rich gas because the main cooling pathways in the present-day interstellar medium involve radiative transitions of carbon, oxygen, and other heavy elements. In a pristine, metal-free interstellar medium, the cooling is dominated by hydrogen and helium molecular emission, which is less efficient. On the other hand, there are processes that could make star formation more efficient in the early universe. The higher density of the universe at early times means that gas densities in early galaxies were higher, which could accelerate star formation. The cosmic microwave background at early times was much warmer than today, providing a thermal floor that prevents the gas from cooling below the CMB temperature, which could change the characteristic mass of stars and the overall star formation efficiency. The population of very massive stars, so-called population 3 stars made of only hydrogen and helium, is expected to be qualitatively different from modern stars, with a distribution extending to much higher masses, potentially hundreds of solar masses. If early galaxies were dominated by population 3 stars and their immediate descendants, the relationship between stellar mass and luminosity would be different from the models assumed in photometric mass estimates, which use stellar population models calibrated on present-day stellar populations. This possibility that the baryonic physics is different, but the dark matter model is correct, is the least radical resolution of the tension. It requires modifications to the astrophysical modeling of galaxy formation, but does not require changes to the cosmological model. Several groups are actively developing models of early galaxy formation that can reproduce the Webb observations within the standard Lambda-CDM framework by allowing more efficient star formation at early times. The second possibility is that the standard Lambda-CDM model correctly describes the baryonic physics, but the dark matter model needs modification. Specifically, if dark matter has properties different from the standard cold, collisionless dark matter assumption, the structure formation history could differ enough from the standard prediction to explain the early massive galaxies. One alternative dark matter model that has received attention in this context is warm dark matter. In warm dark matter models, the dark matter particles have a thermal velocity distribution with a characteristic velocity set by their mass. If the dark matter is warm enough, small-scale structure is suppressed because the thermal motion of the dark matter particles smooths out density fluctuations below a characteristic scale called the free streaming length. Warm dark matter predicts fewer small mass halos than cold dark matter, which is actually a potential solution to several small-scale structure problems with Lambda-CDM, including the too big to fail problem and the satellite galaxy problem. However, Warm dark matter that is warm enough to suppress small-scale structure also predicts fewer large mass halos at early times, because the hierarchical buildup of structure proceeds more slowly. Warm dark matter does not obviously explain the early massive galaxies. If anything, it makes the problem worse by reducing the number of massive halos available to host them. Another alternative is fuzzy dark matter, also called ultralight axion dark matter or wave dark matter. In fuzzy dark matter models, the dark matter is an extremely light scalar particle with a mass of approximately 10 to the minus 22 electron volts, so light that its de Broglie wavelength is of galactic scale, approximately 1 kiloparsec. At this scale, quantum mechanical wave effects, specifically the suppression of structure below the de Broglie wavelength, become important. Fuzzy dark matter suppresses the formation of small-scale halos and produces flat density cores in galactic halos, rather than the cuspy profiles predicted by cold dark matter. Fuzzy dark matter has specific implications for galaxy formation at high redshift. The suppression of small-scale structure in fuzzy dark matter could delay the formation of the first halos and alter the rate at which large halos assemble. Whether fuzzy dark matter can explain the early massive Webb galaxies while remaining consistent with other observational constraints, including the Lyman alpha force power spectrum and CMB observations, is an active research question. The third possibility, and the most radical, is that the standard Lambda-CDM cosmological framework itself needs modification at a more fundamental level. This could involve modifications to the initial power spectrum of density fluctuations from inflation, modifications to the dark energy behavior, or modifications to the expansion history of the early universe. The initial power spectrum could have more power on small scales than the standard nearly scale invariant spectrum predicts if inflation had specific non-standard dynamics during the relevant period. More power on small scales means more density fluctuations of the right amplitude to form massive halos earlier. If the primordial power spectrum has a feature, a specific enhancement, at the scales corresponding to the early massive galaxies, this could explain their abundance without requiring changes to the dark matter or the baryonic physics. This is intriguing because current CMB observations only constrain the primordial power spectrum down to scales corresponding to angular scales on the sky of approximately a few arc minutes. Smaller scales are not accessible to the CMB because of silk damping, the process by which photon diffusion in the early universe erases fluctuations on small scales. The primordial power spectrum could have significant features on small scales corresponding to the galaxy formation scales probed by Webb without violating any current CMB constraints. The dark energy behavior could also affect early galaxy formation if the dark energy density at early times was different from the constant value assumed in the standard model. Early dark energy models, which were proposed to resolve a different tension in cosmology, the Hubble tension that I will describe shortly, predict higher dark energy density at early times that affects the expansion rate and hence the growth of structure. Some models of early dark energy could enhance the number density of massive early galaxies. There is another and entirely separate observational anomaly that the James Webb Space Telescope has not created, but has sharpened the Hubble tension. This is the discrepancy between two independent measurements of the current expansion rate of the universe, called the Hubble constant, or H0, and it has become the central unresolved tension in modern cosmology. The Hubble constant is the rate at which the universe is expanding at the present epoch. It is defined as the recession velocity of a galaxy divided by its distance. H0 equals V divided by D. In an expanding universe, galaxies that are further away appear to recede faster, and the ratio of recession speed to distance is a constant, the Hubble constant, at any given moment in cosmic time. The Hubble constant has units of kilometers per second per megaparsec. The measurement of the Hubble constant from the late universe uses the cosmic distance ladder. The first rung of the ladder is geometric, distances to nearby Cepheid variable stars measured by parallax, where the apparent shift in the star's position during the Earth's orbit around the Sun directly gives the distance through trigonometry. Cepheids are pulsating stars whose period luminosity relationship, the fact that more luminous Cepheids pulsate more slowly, was discovered by Henrietta Swan Leavitt in 1908. By calibrating the Cepheid period luminosity relationship with parallax distances, astronomers can use Cepheids as standard candles. Measuring a Cepheid's pulsation period gives its intrinsic luminosity, and comparing this to its apparent brightness gives its distance. The second rung uses Cepheids in nearby galaxies to calibrate type Ia supernovae, which are thermonuclear explosions of white dwarf stars that have a characteristic maximum luminosity. Type Ia supernovae are visible across cosmological distances because they are intrinsically extremely luminous, reaching peak absolute magnitudes of approximately -19. By calibrating the supernova luminosity with Cepheid distances to nearby supernova host galaxies, and then using supernovae to measure recession velocities at large distances where the Hubble flow dominates over peculiar motions, astronomers can measure H0. The SH0-ES collaboration, led by Adam Riess at Johns Hopkins University, has refined this measurement over more than a decade using the Hubble Space Telescope for the Cepheid observations. Their most recent measurement gives H0 equals 73.04 plus or minus 1.04 kilometers per second per megaparsec, a precision of approximately 1.4%. The measurement of the Hubble constant from the early universe uses the cosmic microwave background. The CMB encodes the physics of the last scattering surface when the universe was approximately 380,000 years old, in the pattern of temperature fluctuations on the sky. The physical scale of the acoustic peaks in the CMB power spectrum, the angular scale at which the temperature fluctuations are enhanced, is set by the size of the acoustic horizon at last scattering, which is a known function of the cosmological parameters. By measuring the angular scale of the CMB acoustic peaks, which requires no assumptions about the distance ladder, and by fitting the full CMB power spectrum with the Lambda-CDM model, the Planck collaboration has derived H0 equals 67.4 plus or minus 0.5 kilometers per second per megaparsec, a precision of approximately 0.7%. The two measurements, 73.04 and 67.4, differ by 5.6 kilometers per second per megaparsec, or approximately 5 sigma, 5 standard deviations from what would be expected if the measurements were drawn from the same true value. The probability of obtaining a discrepancy this large by chance, if both measurements are correct and the standard model is right, is approximately 1 in 3 million. The Hubble tension has been one of the most intensively studied problems in cosmology since approximately 2016. When the precision of the measurements first made it statistically significant at the 3 sigma level, it has now reached 5 sigma. Hundreds of papers have been written examining each step of the distance ladder for potential systematic errors, proposing modifications to the cosmological model, and testing alternative distance indicators. The Gaia satellite, the European Space Agency mission that has measured parallax distances to billions of stars with extraordinary precision, has been used to recalibrate the parallax zero point of the Cepheid distance scale. The Gaia calibration has been incorporated into the SH0-ES analysis without significantly reducing the tension, the tip of the red giant branch method, an independent distance indicator based on the known luminosity at which low-mass stars reach the tip of the red giant branch as they exhaust their hydrogen and ignite helium burning, has been used by independent groups as an alternative first rung of the distance ladder, the TRGB-based H0 measurements give results spanning approximately 69 to 73 kilometers per second per megaparsec, with the most precise measurements being somewhat below the SH0 ES Cepheid-based value, but still above the Planck value. Gravitational wave standard sirens provide an entirely independent measurement of H0. The gravitational wave signal from a compact binary merger contains information about the masses and distance of the system, allowing the distance to be measured directly from the gravitational waveform without any calibration against astronomical distance indicators. The electromagnetic counterpart, the kilonova or gamma ray burst associated with the merger, provides the redshift of the host galaxy. H0 is then measured as the ratio of the inferred recession velocity to the gravitational wave distance. The first gravitational wave standard siren measurement from GW170817 and its electromagnetic counterpart gave H0 equals 70 plus 12 minus 8 kilometers per second per megaparsec, consistent with both the Planck value and the SH0 ES value within the large uncertainty. As more binary neutron star mergers are detected by LIGO and Virgo and their counterparts are identified, the gravitational wave standard siren measurement will improve, eventually reaching a precision of a few percent and providing a definitive independent measurement. The James Webb Space Telescope has now entered the Hubble constant measurement. Adam Rees and the SH0 ES team used Webb's NIRCam to observe Cepheids in the same nearby galaxies that were used for the Hubble-based Cepheid calibration. The motivation was to test whether crowding effects, the blending of the Cepheid light with that of nearby stars in the dense environments of spiral galaxies, could be a systematic error in the Hubble measurements that would not be detected by Hubble due to its inferior angular resolution. Webb's superior angular resolution in the infrared, approximately 0.65 arcseconds per pixel compared to Hubble's 0.1 arcseconds per pixel, combined with its sensitivity in the near infrared, where Cepheid contamination from background galaxies and stellar populations is lower, should be able to detect and correct for any crowding effects. The Webb Cepheid measurements, published by Rees and collaborators in 2023, confirmed the Hubble-based Cepheid measurements without finding significant crowding effects. The tension with the Planck CMB value persists at high statistical significance. If the Hubble tension is not a systematic error in either measurement, it implies that the standard Lambda-CDM model is incorrect. The model cannot simultaneously fit the early universe CMB observations and the late universe expansion rate observations. The early galaxy problem, the Hubble tension, are independent observational anomalies, each suggesting that the standard Lambda-CDM model may be incomplete. Their combination makes the case for new cosmological physics stronger. If the model has problems in two independent regimes, the early galaxy formation era and the late universe expansion rate, the likelihood that both arise from systematic errors in the observations is smaller than if only one anomaly existed. The emerging picture that connects these anomalies is that the standard model may be underestimating how quickly structure formed in the early universe. Both the early massive galaxies, which require rapid structure assembly in the first billion years, and the Hubble tension, which requires faster expansion than the CMB model predicts, could be symptoms of the same underlying modification to the cosmological model. A universe that expands faster at early times and forms structure more rapidly than the standard Lambda-CDM model predicts. The 12 principles in my book address exactly this kind of scientific situation. How to think clearly about anomalies, how to distinguish real signals from systematic errors, and how to maintain intellectual honesty about what the data does and does not show. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me describe the most promising theoretical proposals for modifying the cosmological model in ways that could resolve both tensions simultaneously, because this is where the research is most active and where the connection to fundamental physics is clearest. Early dark energy is the most studied proposal. In early dark energy models, the cosmological constant is replaced by a dynamical scalar field that has a non-negligible energy density in the early universe around the time of matter radiation equality before decaying to negligible density at later times. The higher expansion rate at early times, driven by the extra dark energy contribution, increases H0 because a given CMB angular scale corresponds to a shorter physical distance when integrated over a faster expanding universe, and a shorter distance requires a higher H0 to match the observed angular scale. The specific early dark energy model proposed by Poulin, Smith, Carwall, and Kamionkowski uses a scalar field with an axion-like potential, with the field initially frozen by Hubble friction, and then rolling and diluting after the Hubble rate drops below the field mass. This model can increase H0 by approximately 2 to 3 kilometers per second per megaparsec, moving it in the direction of resolving the tension, though typically not enough to fully resolve it without additional modifications. Early dark energy models make specific predictions for the CMB power spectrum, including changes to the acoustic scale and specific signatures in the polarization spectrum that can, in principle, be tested with more sensitive CMB observations. The Atacama Cosmology Telescope and the South Pole Telescope have provided updated CMB data that constrain early dark energy models with results that are somewhat in tension with the most common early dark energy parameterizations, but do not rule them out. Interacting dark energy, in which dark matter and dark energy exchange energy, or momentum, is another proposal. Specific interacting dark energy models can modify the expansion history and the growth of structure in ways that could explain the Hubble tension while also affecting early galaxy formation. The challenge is finding models that modify the early universe in the right direction without simultaneously creating new tensions with other observations, such as the matter power spectrum measured by weak gravitational lensing surveys. Modified gravity is a broader class of modifications to the cosmological model. In standard cosmology, gravity is described by general relativity. Various extensions of general relativity, including FR gravity, scalar tensor theories, and massive gravity, predict different expansion histories and different growth rates for cosmic structure. Some of these modifications could, in principle, explain both the Hubble tension and the early galaxy problem, but finding a specific model that resolves both tensions while remaining consistent with all other observational constraints, including CMB, baryon, acoustic oscillations, gravitational waves, and solar system tests of gravity, is a significant challenge. Primordial black holes are another speculative but interesting possibility. If a significant fraction of the dark matter consists of primordial black holes formed in the early universe, the structure formation history would differ from the standard CDM picture. Primordial black holes act as seeds for early structure formation, potentially enabling massive halos to form earlier than standard CDM predicts. Primordial black holes at mass scales that would make them relevant for galaxy formation have been constrained by various observations, including microlensing surveys and CMB spectral distortions, but there remain mass windows where they could be significant. Beyond the massive galaxy tension and the Hubble tension, the James Webb Space Telescope has generated 2 additional lines of evidence that challenge or constrain our understanding of the early universe. The discovery of active galactic nuclei at extraordinary redshifts and new constraints on the epoch of reionization. Active galactic nuclei, AGN, are the bright cores of galaxies that harbor actively accreting supermassive black holes. As gas falls into a supermassive black hole, it forms a hot accretion disk that radiates across a broad range of wavelengths, from radio waves to X-rays. The most luminous AGN, called quasars, can outshine their host galaxies by factors of thousands and are visible across cosmological distances. The formation of supermassive black holes with masses of 10 to the 8 to 10 to the 9 solar masses within the first billion years of the universe's history, which had been established by ground-based quasar surveys before Webb, was already a significant challenge to standard formation models. A black hole of 10 to the 9 solar masses must grow from an initial seed, either a stellar mass black hole of 10 to 100 solar masses, or a more massive direct collapse black hole of 10 to the 5 to 10 to the 6 solar masses, through accretion. If the accretion proceeds at the Eddington rate, the maximum rate allowed by radiation pressure, the doubling time for the black hole mass is approximately 50 million years. Starting from a stellar mass seed at a redshift of 30 and accreting at the Eddington rate continuously, the black hole reaches 1 billion solar masses at a redshift of approximately 7, barely within the window allowed by the quasar observations. Webb has extended this problem in two directions. First, it has detected AGN at higher redshifts than any previous observation, with spectroscopically confirmed AGN at redshifts above 10 harboring black holes of 10 to the 7 to 10 to the 8 solar masses. These objects must have been accreting at or above the Eddington rate from very massive seeds, or through super Eddington accretion episodes, to reach their observed masses within the available time. Second, and more surprisingly, Webb has found a population of AGN at redshifts 4 to 6 that are much more numerous than expected, and that appear to be hosted in galaxies with relatively small stellar masses. These objects, sometimes called little red dots because of their compact morphology and red colors in Webb photometry, are intriguing because they suggest that black hole growth in the early universe was closely connected to and possibly preceding the buildup of the host galaxy's stellar mass. In the standard picture of galaxy black hole coevolution, galaxies and their central black holes grow together in a correlated way, with the black hole mass being approximately 0.1 to 0.3% of the galaxy's stellar mass. This correlation is observed in the present-day universe across many orders of magnitude in galaxy mass. If the little red dots have black holes that are massive relative to their host galaxy stellar mass, they represent an early universe in which the black holes grew first before the stars, which is not the standard picture. The epoch of reionization is the period in cosmic history when the first stars and galaxies ionized the neutral hydrogen that filled the universe after recombination. The universe emerged from the Big Bang in a hot, ionized state. As it cooled, electrons and protons combined to form neutral hydrogen at a redshift of approximately 1,100, the last scattering surface observed as the CMB. The universe then entered the cosmic dark ages, a period of hundreds of millions of years with no luminous sources, during which the intergalactic medium was neutral. The formation of the first stars and galaxies ended the cosmic dark ages and began reionizing the neutral hydrogen, first in bubbles around individual sources, then in larger ionized regions that grew and merged until the intergalactic medium was fully ionized at a redshift of approximately 6, corresponding to the universe being about 900 million years old. The reionization history, specifically the redshift at which reionization was complete, and the nature of the dominant ionizing sources, has important implications for early galaxy formation. If the early massive galaxies detected by Webb were the primary ionizing sources, their radiation output must be consistent with the observed reionization history. If they are too numerous and too luminous, they would have reionized the universe too early, inconsistent with observations of the neutral fraction at redshift 6 to 7 from quasar spectra. Webb has provided new constraints on the reionization history through deep spectroscopy of high redshift galaxies. The detection of Lyman alpha emission from galaxies at redshifts above 7 provides information about the neutral fraction of the surrounding intergalactic medium because Lyman alpha photons are absorbed by neutral hydrogen. In the early JADE spectroscopic results, a surprisingly high fraction of galaxies at redshifts 7 to 9 show strong Lyman alpha emission, suggesting that the intergalactic medium around them was more ionized than the standard reionization models predict at those epochs. This is another potential tension with the standard model. The intergalactic medium appears to have been ionized earlier and more completely around the early massive galaxies than expected. This could be explained by the galaxies themselves, if they are more efficient ionizers than assumed, or by the topology of reionization, which may have proceeded inhomogeneously, with some regions being fully ionized while others remained neutral. The combination of the early massive galaxy tension, the Hubble tension, the early supermassive black hole tension, and the early reionization constraints paints a picture of the early universe that is more active, more structured, and more evolved than the standard Lambda-CDM model predicted. The accumulated evidence from Webb's first 2 years of operation does not overturn the standard model, but it places it under pressure from multiple independent directions simultaneously. This is exactly the kind of situation that has historically preceded major revisions to the theoretical framework. The discovery of the accelerating expansion of the universe in 1998 was based on a single population of observations, type Ia supernovae at high redshift, but it was confirmed rapidly by independent CMB and baryon acoustic oscillation measurements. The Hubble tension and the early galaxy tension are based on independent observations with independent instruments and independent analysis techniques, and they are pointing in the same direction. The standard model appears to underpredict the rate of structure formation at early times. What is particularly interesting about the early galaxy tension from a theoretical perspective is that the problem cannot be solved simply by modifying the astrophysical modeling of galaxy formation. Even if you allow the most extreme possible star formation efficiency, converting all available baryons to stars with no feedback losses, you run up against the fact that the dark matter halos available to host these galaxies are predicted to be far less massive than required at those redshifts. The problem is not just the star formation efficiency. It is the total mass of dark matter assembled by those early times. If the dark matter halos are not massive enough to host the observed galaxies, then either the dark matter model is wrong, in the sense that structure assembles faster than cold dark matter predicts, or the initial power spectrum has more power on the relevant scales than the standard nearly scale invariant spectrum provides, or the standard assumption of adiabatic Gaussian initial conditions is incomplete. Each of these possibilities connects to fundamental physics in a different way. Modified dark matter, whether warm, fuzzy, or self-interacting, changes the transfer function that maps the primordial power spectrum to the distribution of dark matter halos. Enhanced small-scale power connects to non-standard inflationary dynamics. Non-Gaussian or non-adiabatic initial conditions connect to physics beyond the simplest single-field inflation models. The James Webb Space Telescope was not designed to test these specific hypotheses. It was designed to study the earliest galaxies and to characterize their properties. But the data it is generating is constraining these hypotheses at a level of precision that no previous observatory could achieve, and the constraints are interesting. Let me now describe how this situation is likely to resolve over the next 5 to 10 years, as more Webb data accumulates and as complementary observations from other facilities constrain the theoretical interpretations. The most important near-term development is the accumulation of spectroscopic redshifts and stellar mass estimates for the early massive galaxy candidates. Webb's NIRSpec multi-object spectrograph will continue to observe the most promising galaxy candidates from the imaging surveys, providing spectroscopic confirmation of their redshifts and independent stellar mass estimates from emission line diagnostics. As the number of spectroscopically confirmed early massive galaxies grows, the statistical significance of the tension with the standard model will either increase or decrease. Parallel development of more sophisticated stellar population models, specifically models that account for the possibility of bursty star formation histories, population 3 stars, top-heavy initial mass functions, and strong nebular emission from intense star formation, will allow more accurate conversion from observed photometric properties to stellar masses. If these improved models systematically reduce the inferred stellar masses, the tension will decrease. If they do not, the tension is robustly established. The Hubble tension will be further tested by additional gravitational wave standard siren measurements from LIGO, Virgo, and the planned LIGO India detector by the Carnegie Chicago Hubble program, and other independent distance ladder analyses, and by weak gravitational lensing surveys from the Euclid satellite and the Vera Rubin Observatory's LSST. If the tension persists at 5 sigma as these independent measurements accumulate, the probability that it is a systematic error in any specific measurement becomes extremely small. Theoretical model development will continue to explore the parameter space of modifications to Lambda-CDM. Early dark energy models, axion dark matter models, primordial magnetic fields, and other proposed modifications will be tested against the growing observational dataset. Bayesian statistical analyses combining all available observational constraints will identify which modifications can simultaneously resolve multiple tensions and which are ruled out. The most likely outcome of this scientific process, based on the history of cosmology, is not a complete replacement of the standard model, but a revision of it. The Lambda-CDM framework will likely survive with additional parameters or modified components. Perhaps a slowly evolving dark energy instead of a cosmological constant. Perhaps a modified dark matter model that forms structure slightly faster at small scales. Perhaps a modification to the early expansion history. Whether the modification will involve genuinely new fundamental physics, as dark energy did in 1998, or will be a refinement of the existing framework is not yet known. What is clear is that James Webb is doing exactly what it was designed to do, pushing observational cosmology to its limits, revealing the universe at earlier times and with more detail than any previous instrument, and confronting our theoretical models with data that they were not calibrated against. The specific problems it has revealed, the early massive galaxies, the early black holes, the early reionization, are genuine scientific problems that will drive theoretical progress for years to come. This is the correct statement about what Webb has found a problem with. Not our universe, in the sense of the universe itself being broken or wrong, but our model of the universe, which, like all models in science, is an approximation that works in the regime it was designed for and shows its limitations when pushed to new extremes. The universe is not hiding from us. It is revealing itself in infrared photons from 13 billion years ago to an instrument that was built with exactly this purpose. The 12 principles in my book address the relationship between observation, theory, and the revision of knowledge that occurs when new observations push beyond the boundaries of existing models. This is one of the most exciting moments in the history of cosmology, and understanding what Webb is telling us requires exactly the kind of clear thinking those principles are designed to provide. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What do you think the early massive galaxy tension is telling us? Is it a problem with the standard model or with our models of star formation and galaxy assembly? Tell me in the comments. The telescope completed its first year of science operations in July 2023, having spent approximately 6,000 hours of science time on a diverse program of targets from the solar system to the high redshift universe. The first year's data, now publicly available through MAST, the Mikulski Archive for Space Telescopes, has been analyzed by hundreds of independent research groups worldwide. The scientific results continue to accumulate. Beyond the early massive galaxy tension, Webb has found specific evidence for the rapid assembly of the first supermassive black holes, with active galactic nuclei detected at redshifts above 10 that harbor black holes of 10 to the 7 to 10 to the 8 solar masses. These early black holes are as challenging to explain as the early massive galaxies. Forming a 100 million solar mass black hole within 500 million years of the Big Bang requires extremely rapid growth. From a massive seed or continuous near-Eddington accretion from a smaller seed for hundreds of millions of years. Webb has also found evidence for early dust, complex organic molecules, and metallicities in early galaxies that suggest rapid chemical enrichment, all indicating that the first stars lived fast and died violently, enriching the interstellar medium with heavy elements very quickly. These observations paint a picture of the early universe as a place of extraordinary intensity, where the first structures formed and evolved faster than our standard model expected. The overall picture that is emerging from the first 2 years of Webb science is that the early universe was more active, more structured, and more chemically evolved than the standard Lambda-CDM model predicted. The discrepancies are not at a level that requires a revolution in cosmology. They are at a level that suggests significant revision of the astrophysical models of galaxy formation, possibly combined with modifications to the cosmological model. The specific scientific process underway is careful and methodical. Teams are measuring spectroscopic redshifts for the photometrically selected early massive galaxy candidates, determining which candidates are genuine high redshift galaxies and which are low redshift interlopers. Teams are developing more sophisticated stellar population models that account for the specific conditions of the early universe, including the contribution of nebular emission, the effect of binary stellar evolution on the integrated light, and the potential for top-heavy initial mass functions. Teams are comparing the photometrically inferred stellar masses to those derived from spectroscopic line diagnostics, which provide independent constraints. This is how science actually works when it encounters an anomaly. Not a single paper claiming the model is wrong, but a sustained, collaborative process of measurement, analysis, cross-checking, and theoretical interpretation that converges over years on a correct understanding. The James Webb anomaly is in this process now. The answer is not yet known. But the question is sharper, more precisely defined, and better observed than any previous probe of the very early universe has allowed. What I find most interesting about the James Webb anomaly as a physicist is not the specific numbers, though the numbers are striking. It is what the anomaly reveals about the state of cosmological knowledge. The standard Lambda-CDM model was never intended to be a complete theory of the universe. It is a framework that parameterizes our ignorance about dark matter, dark energy, and the initial conditions from inflation with a small number of measurable parameters. The model has been extraordinarily successful because its predictions, derived from these few parameters, match an enormous body of observations with high precision. But every successful model eventually encounters its limits. The limits are where the new physics is. The early galaxy tension and the Hubble tension are, so far, the most significant indications that the Lambda-CDM model has encountered its limits. The model may need extensions in the form of modified galaxy formation physics, Or it may need more fundamental modifications involving the nature of dark matter, or dark energy, or the primordial power spectrum. The James Webb Space Telescope is not going to tell us which of these is needed in a single observation. It is going to accumulate the specific data that, when combined with theoretical understanding, will point the way. The history of cosmology in the 20th century is a history of observations that extended far beyond what was expected and revealed structures and phenomena that required new physics to explain. The discovery of the accelerating expansion in 1998 required dark energy, an entity that was not anticipated by any prior theory. The discovery of the flat geometry of the universe from CMB observations required inflation, an early period of exponential expansion that was theoretical speculation before the observations confirmed its predictions. The discovery of large-scale structure from galaxy surveys required cold dark matter, a new form of matter not included in the standard model of particle physics. James Webb may be the telescope that reveals the next entry in this list. The early massive galaxies, the rapid formation of supermassive black holes, the unexpectedly early chemical enrichment, and the Hubble tension in combination may point toward a modification of the cosmological model that will require new physics, either in the dark sector, or in the initial conditions, or in the fundamental physics of gravity and dark energy. What that new physics is, we do not yet know. But the telescope is working, the data is flowing, and the anomalies are real. The universe is not hiding its structure from us. It is revealing it in infrared light from 13 billion years ago to a telescope floating in the cold darkness at the second Lagrange point, 1.5 million kilometers from the planet that built it. The 12 principles in my book include exactly the kind of framework for thinking about these questions. How to interpret anomalies without overstating their significance, how to identify when data is pointing beyond the current framework, and how to hold the tension between what we know and what we do not know with intellectual honesty. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What do you think Webb's early galaxy observations are telling us about the standard model? Is it astrophysics or is it new cosmological physics? Tell me in the comments. The James Webb Space Telescope is generating data at an extraordinary rate. The telescope completed its first year of science operations in July 2023, having spent approximately 6,000 hours of science time on a diverse program of targets from the solar system to the high redshift universe. The first year's data, now publicly available through MAST, the Mikulski Archive for Space Telescopes, has been analyzed by hundreds of independent research groups worldwide. The scientific results continue to accumulate beyond the early galaxy question. Let me describe several of the most significant findings from Webb's first 2 years of operation, because they collectively paint a picture of an early universe that is more complex and more active than standard models predicted. Webb's first observations of the deep field were released on the 11th of July 2022, the day before the official science release by President Biden during a White House briefing. The image showed a cluster of galaxies called SMACS 0723 at a distance of approximately 4.6 billion light years, with background galaxies gravitationally lensed by the cluster's mass into arcs and multiple images. The depth reached by Webb in this single pointing, with approximately 12.5 hours of total exposure time, was comparable to Hubble's deepest observations, which required hundreds of hours. The scientific release the following day included a spectrum of the hot Jupiter exoplanet WASP 96b, which showed the clear spectral signatures of water vapor, carbon dioxide, and sulfur dioxide in the planet's atmosphere. The sulfur dioxide was unexpected. Its detection implies photochemical reactions driven by UV light from the host star, a previously undetected process in exoplanet atmospheres. The spectrum was obtained in a single transit observation lasting approximately 6 hours, a sensitivity that would have required months of Hubble observations to approximate. Webb also released a mid-infrared image of the Eta Carinae Nebula, a massive stellar nursery approximately 7,500 light-years away, showing previously invisible structures in the cold dust and gas that surrounds newly forming stars. The mid-infrared capability of the MIRI instrument sees through the dust that obscures star formation in visible light, revealing the dense cores of forming protostars and the filamentary structure of the molecular cloud. These early science observations establish that Webb performs as designed, exceeding its engineering requirements in sensitivity and stability. The telescope's primary mirror is aligned to approximately 150 nanometers of surface quality compared to the design requirement of 400 nanometers. The background level at L2, with the sunshield blocking solar, terrestrial, and lunar light, is lower than expected, improving the depth reached in each observation. For the early galaxy science specifically, Webb has now observed multiple deep fields, including the JADES, Goods S and Goods N fields, the Primer survey, the Cosmos Webb survey, covering approximately 0.54 square degrees, and various other programs. The combined area and depth of these surveys, together with the spectroscopic follow-up from NIRSpec, provides the statistical foundation for robustly measuring the galaxy stellar mass function at high redshift. The Cosmos Webb survey is particularly important for the early massive galaxy question because of its large area. The number density of the most massive early galaxies is low enough that deep pencil beam surveys like JADES may contain only a handful of them. Cosmos Webb covers an area approximately 50 times larger than JADES, allowing the statistical sampling of the rarest and most massive early galaxy candidates. Beyond the galaxy's stellar mass function, Webb is measuring the galaxy size-mass relation at high redshift, finding that early galaxies are more compact than their present-day counterparts of the same mass. A galaxy at redshift 7 with the same stellar mass as the Milky Way would typically be several times smaller in effective radius. This compactness is consistent with the standard model prediction that early galaxies were formed in denser environments, but the degree of compactness and its evolution with redshift provide quantitative tests of galaxy formation models. Webb is also measuring the morphologies of early galaxies in detail. Many early galaxies are not smooth elliptical or disk-like systems, but show complex, irregular morphologies with multiple bright clumps connected by diffuse emission. These clumpy galaxies are interpreted as systems undergoing intense star formation in distinct star-forming regions, consistent with the high specific star formation rates inferred from the photometry. Some early galaxies show evidence for disk-like rotation in their emission line kinematics, measured with NIRSpec, suggesting that rotating disk galaxies formed earlier in cosmic history than standard models predicted. The NIRCam GRISM spectroscopy mode, which provides low-resolution spectra of all objects in the field of view simultaneously, has been used to measure emission line fluxes for thousands of galaxies at once. The emission line fluxes, combined with the imaging photometry, provide star formation rates, gas phase metallicities, and ionization conditions for the galaxy populations at high redshift. The results show that early galaxies have high specific star formation rates, meaning they are forming stars rapidly relative to their stellar mass, and that their gas is highly ionized, consistent with populations of young, hot, massive stars. The metallicities of early galaxies, measured from the ratio of oxygen to hydrogen in the emission lines, are systematically lower than in present-day galaxies, as expected, if the first generations of stars have not yet had time to enrich the interstellar medium with heavy elements through supernova explosions. But some early galaxies show metallicities that are surprisingly high for their redshift, suggesting that chemical enrichment proceeded faster in some systems than standard models predict. These metallicity constraints are relevant for understanding the early massive galaxy tension. If the first galaxies underwent extremely rapid star formation, they would have produced large numbers of massive stars that lived brief lives and exploded as supernovae, rapidly enriching the interstellar medium. The high metallicities of some early galaxies are consistent with this rapid star formation scenario, providing independent evidence that the star formation efficiency was high in the early universe. The first extragalactic planetary nebula detected by Webb in a nearby galaxy demonstrated the instrument's ability to resolve fine details in the emission from ionized gas around dying stars, providing new probes of the chemical enrichment cycle from stellar death to interstellar medium. Webb has also detected carbon chain molecules in protoplanetary disks around young stars, extending the inventory of complex organic chemistry in star-forming regions and informing models of prebiotic chemistry in planetary systems. All of these observations are part of the broader program of early universe science that Webb is enabling. The telescope has fundamentally changed our ability to study the very early universe, and the tensions that have emerged from its observations are not isolated anomalies, but part of a coherent picture of an early universe that was more active than expected. The history of science suggests that the most productive moment in the development of a theory is precisely the moment when accurate observations begin to reveal that the theory's predictions are not quite right. The errors in the predictions are not failures of the theory, they are clues to what the theory is missing. The Lambda-CDM model has been enormously successful, and the tensions revealed by Webb are, in the grand scheme of the model's achievements, relatively small. But small tensions, carefully measured, have historically been the seeds of the most important theoretical advances. The discovery of the tiny anomaly in Mercury's perihelion precession, which was known since 1859, was the observational phenomenon that general relativity was confirmed by in 1915. The perihelion precession discrepancy was approximately 43 arcseconds per century, amounting to less than 1 degree over the entire history of humanity's systematic astronomy. Yet this tiny discrepancy was pointing toward the deepest modification of our conception of space and time that has ever been achieved. The tensions in the Lambda-CDM model revealed by Webb may not ultimately lead to an equally profound revolution. They may be resolved by astrophysical refinements to the galaxy formation modeling, or by modest modifications to the cosmological parameters that are already within the uncertainty range of current measurements. But they may point towards something more fundamental, a modification to the nature of dark matter, or to the early expansion history, or to the primordial power spectrum that has genuine physical significance. The James Webb Space Telescope is the most powerful astronomical instrument ever built, operating at the frontier of the observable universe in time and in space. The problems it may have found with our universe are not problems with the universe itself. They are, more precisely, invitations from the universe to refine our model of it, to improve our physical understanding of it, and to discover whatever it is that we are currently missing. The invitation is extraordinarily interesting. The response will take years of work by hundreds of researchers, and the final answer, whatever it is, will be an improvement on the Lambda-CDM model that explains more, predicts better, and brings us a step closer to the truth of how the universe we inhabit actually came to be. If this changed how you think about the James Webb Space Telescope's findings and what they mean for our understanding of the early universe, if the tension between the observed early massive galaxies and the predictions of the standard cosmological model looks different after understanding the specific physics of galaxy formation and the nature of the Hubble tension, tell me in the comments. Tell me whether you think the resolution lies in the astrophysics of galaxy formation, in modifications to the dark matter model, or in more fundamental changes to cosmology. Tell me whether the combination of the early galaxy tension and the Hubble tension makes you more or less confident that the standard Lambda-CDM model is complete. And subscribe if you want to keep going into the places where the most precise observations in the history of astronomy are confronting the most fundamental questions about the structure and history of the universe.